Welcome to starry cosmos, a point of light no larger than a few pixels has crossed almost the whole history of the universe to reach us. It left a compact young galaxy called MZ14 when the cosmos was only about 280 million years old. The galaxy is real. Its distance has been measured with spectroscopy, and its existence moves the confirmed frontier of observation deeper into cosmic dawn than ever before. Tonight, we will follow that light backward and ask what the James Webb Space Telescope has actually changed. Why the first galaxies seem so bright, how oxygen and nitrogen appeared so quickly, where the earliest black holes came from, and whether any of this truly breaks our picture of the universe. Dim your lights, settle in, get comfortable, and let us begin. If these quiet journeys help you drift off, hit that like button and subscribe to Starry Cosmos so that the next journey through the vast expanse finds you when you need it. Let us settle in now. Let your awareness drift. Allow yourself to be drawn into a stillness that remembers everything and nothing at once. Consider the immense span of time involved, the unimaginable distances across which we are connecting, simply by existing in this present moment. Let us begin our journey into the earliest moments of the universe, a realm before stars, before galaxies as we know them, even before the familiar structures of matter as we understand it today. We are heading towards an interval rather than an instant to contemplate what is known as cosmic dawn. It was not a singular switch on, but a gradual transformation, a slow exhale following an equally profound contraction. Think of it as the quiet after a great, silent storm. It all began roughly 380,000 years after the Big Bang, a timescale so vast that our everyday thinking struggles to grasp its magnitude. At this point in time, the universe had cooled sufficiently for electrons and protons to combine, forming neutral hydrogen atoms. This event, known as recombination, released a flood of photons, the very first light from the cosmos, which we now observe as the cosmic microwave background, that faint afterglow stretching across all of space like an ancient, ethereal blanket. It is detectable today, a subtle temperature variation imprinted on the radiation itself, a ghostly echo of creation. Feel the residual warmth, the distant memory of when all things were unified in this radiant light, before the universe truly began to separate. Following recombination, we entered what is often referred to as the Dark Ages. This was not simply darkness. It was an epoch dominated by neutral hydrogen, vast clouds of gas suspended throughout space. The early universe was primarily composed of dark matter, a mysterious substance that interacts only through gravity, forming the scaffolding upon which everything else would eventually build. And yet, there were no established stellar light sources to illuminate this period. No stars had ignited, no galaxies had coalesced. It is important to recognize this was not an absence of something, but rather a state of quiescence. A quiet waiting, a necessary prelude to the spectacle that would soon unfold. It was, for all intents and purposes, a deep, pervasive twilight. We call it the cosmic dark ages. And though there are other descriptive terms tossed about, this is the standard terminology used within the scientific community, a useful way to delineate this crucial period of cosmic history. Now consider the boundaries between these epochs. Recombination marks the beginning. Cosmic dark ages is the waiting time between then and dawn. And what follows that epoch is equally important: the emergence of first light, the birth of stars, and ultimately reionization. Astronomers infer the existence of both cosmic dawn and reionization through careful analysis of redshifted light, light stretched by the expansion of the universe, a stretching effect known as cosmological redshift. By studying how light from distant galaxies has been shifted towards longer wavelengths, we can estimate their distance and, consequently, their age. Similarly, signatures of neutral hydrogen, specifically the depletion of hydrogen in the spectra of distant quasars that acted like cosmic beacons, provide crucial evidence for the processes occurring during reionization. It is tempting to imagine a single moment where the first star flared into existence, illuminating the entire darkness. However, it is far more nuanced than that. The formation of the very first stars likely occurred in denser regions of dark matter, gravitational wells that pulled together gas and dust, initiating the process of nuclear fusion within their cores. These early stars were probably massive, burning incredibly brightly and rapidly. But crucially, they were not numerous. They were scattered throughout space, like sparks in a vast, darkened field. Their light was initially absorbed by the surrounding hydrogen, hindering its ionization, preventing it from becoming fully ionized. It is important to remember that the process of reionization was not instantaneous. It was a gradual escalation, spanning hundreds of millions of years as these early stars continued to ignite and seed their environment with heavier elements, elements forged in their nuclear furnaces and dispersed through supernova explosions. Cosmic dawn and reionization are not entirely separate events. They overlap considerably within the timeline. The initial bursts of light from the first stars began to ionize hydrogen, but it was a slow, patchy process. As more and more stars formed, the ionization gradually increased, eventually pushing the entire universe towards a state of near-full ionization. We are still piecing together exactly when this transition occurred, but current evidence places reionization broadly between roughly 150 to 200 million years and 1 billion years after the Big Bang. The details remain uncertain, shrouded in the immense distances and redshifted light that characterize these early epochs, a challenge for any observer. Dark matter continues to play a pivotal role throughout this entire process. As gravity amplified fluctuations in density within the dark matter distribution, these denser regions served as seeds for future galaxy formation. The first stars formed within these nascent galaxies, gradually accumulating more and more material over time. It is an intricate dance between gravity, radiation, and the fundamental forces of nature, a ballet performed on a scale that defies human comprehension. Consider, too, the implications of this early period for our understanding of cosmology as a whole. The abundance of light elements, hydrogen, helium, and lithium, observed today provides crucial constraints on models of Big Bang nucleosynthesis. The fact that these abundances match current observations suggests that the conditions in the very early universe were remarkably precise, a testament to the underlying laws governing the cosmos. But there are still open questions. How did the first black holes form? What was the role of supermassive black holes in seeding galaxy formation? And how does the distribution of dark matter influence the evolution of cosmic structure? These remain some of the most profound mysteries facing cosmologists today. Questions that require continued observation and theoretical development. After recombination released the cosmic microwave background, neutral hydrogen filled the cosmic dark ages until the first stellar populations began cosmic dawn and the overlapping process of reionization. The universe began in darkness, then slowly awakened to light, a journey that continues to unfold even now. It is a reminder of our place within an extraordinary timeline and the incredible potential for further discovery as we continue to push the boundaries of knowledge, seeking ever deeper into the shadows of the past. And perhaps, in understanding these ancient beginnings, we begin to better understand our own present and the future yet to come. Allowing yourself now to settle more fully into this quiet contemplation. Cosmic dawn was not a single sunrise. It was a long, uneven brightening across a universe that had been dark for tens of millions of years. If you are seeking to understand the era when the first stars and galaxies began to shine, then let us turn our gaze toward the James Webb Space Telescope. For decades, astronomers have sought the faintest whispers of light from those nascent galaxies. And it is through the careful measurement of these faint signals that we are beginning to piece together the story of cosmic dawn. A central concept here is redshift, a phenomenon intimately tied to the expansion of space itself. It is not simply the effect of interstellar dust scattering blue light, though that can certainly influence colors. Cosmological redshift represents a fundamental shift in how we perceive the universe's history. Consider the journey of light from these ancient galaxies, vast distances separating us from their origins. As this light travels through an expanding cosmos, it is stretched along with space. This stretching does not diminish the energy carried by the light. Instead, it alters its wavelength. The longer wavelengths shift towards the red end of the spectrum, hence the name redshift. The amount of this stretching is quantified by a number called C, known as the cosmological redshift. It is not a simple linear relationship. The higher the value of C, meaning the more stretched the light, the greater the wavelength shift. This factor, 1 plus C, dictates how much the original ultraviolet light has been lengthened during its voyage across billions of years. Your mind may conjure images of a color filter being placed over an image, but this is far more profound. It is the expansion of space itself, reshaping the fundamental properties of the photons we observe. Now, imagine trying to identify these incredibly distant galaxies. The light they emit is extremely faint and often heavily obscured by dust, within our own Milky Way galaxy, as well as from intervening gas clouds. So how do astronomers find them? Photometric candidates are identified primarily through their colors, the particular combinations of red, green, and blue that we detect with telescopes. You will notice distinctive spectral breaks, subtle shifts in color corresponding to specific elements absorbing light at different wavelengths. These breaks can indicate a galaxy undergoing significant chemical enrichment as it forms, a process where heavier elements forged within stars are scattered into the surrounding space. However, these color signatures alone are not definitive proof. They are susceptible to contamination from nearer objects, galaxies, or even individual stars that simply appear similar in their observed colors. To truly confirm a candidate galaxy's distance and understand its composition, we turn to spectroscopy, essentially dissecting light into its component colors. When the light of a distant galaxy passes through an instrument like NIR spec aboard Webb, it is split into a rainbow of wavelengths. The patterns within this spectrum reveal much more than just color. It reveals the elements present in that galaxy and, crucially, how strongly they are absorbing specific wavelengths. These absorption lines, dark bands against a bright background, act like fingerprints, uniquely identifying different chemical elements. A strong, sharp emission line indicates a particularly intense source of light at that wavelength, offering an incredibly precise measurement of distance. By comparing the observed redshift with the known speed of light, which is remarkably constant across the universe, we can calculate how much farther away these objects are than they appear to be. The history of this concept stretches back to Vesto Slipher in the early 20th century, who painstakingly measured the redshifts of many spiral nebulae. What we now know were galaxies observing that they all appeared to be. Later, Edwin Hubble established a clear relationship between redshift and distance. The farther away a galaxy is, the faster it is receding. However, Slipher's initial observations were largely qualitative. Webb, with its unprecedented sensitivity, allows for quantitative measurements of immense precision. Webb's extraordinary infrared capabilities stem from its unique location at Lagrange point L2, roughly 1 million miles beyond Earth, and in a region where the sun's gravitational pull balances the Earth's. Behind an enormous multi-layered sunshield, Webb remains astonishingly cold. This is absolutely vital because extreme temperatures would interfere with the delicate operation of its infrared instruments. Unlike ground-based telescopes that sit stationary, Webb orbits around L2, constantly adjusting its position to maintain optimal thermal stability and give it a clear view of the deep cosmos. This carefully managed environment allows the telescope's detectors to gather faint infrared light without being overwhelmed by their own heat. Specifically, NIR-CAM near-infrared camera is optimized for detecting extremely faint red light, the kind emitted by the earliest galaxies. It searches for these candidates based on their colors and those spectral breaks mentioned earlier. Then, NIR-SPEC near-infrared spectrograph takes over. It meticulously analyzes the spectra of these candidates to precisely measure their redshifts. MIRI mid-infrared instrument, with its even longer wavelength capabilities, is designed to study cooler objects like dust-shrouded galaxies and molecular clouds where stars are born. MIRI works in tandem with NIR-SPEC and NIR-CAM to build a comprehensive picture of the cosmos. Each instrument addresses a different piece of the puzzle. NIR-CAM identifies potential candidates by color. NIR-SPEC verifies their distance t. The combined data from these instruments are not simply observations. They are pieces of a complex, interwoven narrative. By carefully accounting for the effects of dust and gas along our line of sight, as well as correcting for variations in the expansion rate of the universe, a phenomenon known as Hubble tension, which is currently an active area of research. Astronomers can construct increasingly accurate maps T. It is a slow, painstaking process built on relentless observation and rigorous analysis, but one that promises to unveil the grandest secrets of the cosmos. A red dot can begin the search, but a spectrum is what lets the universe show its work. If you find yourself drawn to the echoes of the universe's earliest moments, let us consider a remarkable discovery unveiled by the JWST, Advanced Deep Extragalactic Survey, or JADES. This ambitious project represents an extraordinary effort to peer back into the infant cosmos, driven by the desire to understand how galaxies, and indeed our own Milky Way, began to take shape just a few 100 million years after the Big Bang. It is a journey that demands patience and precision, a gradual unveiling of secrets held within the faint light of the distant past. And now, let us turn our attention specifically to JADES Open's Redshift 14, a particularly compelling chapter in this ongoing exploration. The JADES survey itself is designed to systematically observe hundreds of galaxies at extremely high redshifts, numbers which represent how much the light from those objects has been stretched by the expansion of the universe as it moves away from us. These redshifts are not simply measurements of distance, but rather clues about an object's velocity and age. A higher redshift implies a greater distance and, consequently, a younger era in its history. The survey utilizes both infrared and optical capabilities, seeking to capture as much information as possible within each distant galaxy. But this particular story centers on what was achieved with the near-infrared spectrograph, or NIR spec, aboard JWST, an instrument exquisitely sensitive to the faint infrared light emitted by these primordial galaxies. It began with a team led by Dr. Francesco Carniani and published in a series of papers detailing observations made through NIR spec. They meticulously analyzed data from JADES, identifying two particularly luminous galaxies that stand out against the backdrop of this ancient epoch. Galaxies JADES GSC 14.0 and JADES GSC 13.5. These were not simply bright spots in the sky. They exhibited remarkable redshifts, measured using the shift in their spectral lines of 14.32 plus, or minus 0.0007. A truly astounding figure when contemplating the time scale of cosmic history. This redshift indicated that the light we are observing from these galaxies had traveled over 14 billion years to reach us, meaning they existed approximately 300. Crucially, it was not just a single measurement. Carniani and his collaborators reported redshift measurements of 13.90 plus, or minus 0.17 for JADES GSC 13.5, providing complementary data that strengthened the initial findings. The NIR spec instrument's precision is paramount here. It allows scientists to precisely measure the spectral lines emitted by elements within these incredibly distant galaxies: hydrogen, oxygen, helium. And by analyzing the shifts in those lines, they can determine the redshift, and thereby the distance and age of the object. What was particularly intriguing about JADES GSC 14.0, the galaxy with the redshift of 14.32, was its unexpectedly resolved spatial structure. Using JWST imaging capabilities, astronomers were able to discern details within the galaxy itself, a phenomenon rarely observed at such extreme distances. The observations revealed that it was dominated by a broad stellar continuum, suggesting that it was primarily composed of stars, rather than being overwhelmingly influenced by an active galactic nucleus, a supermassive black hole violently feeding on surrounding material. This finding is significant because for decades, astronomers have hypothesized that the brightest galaxies in the early universe were powered by incredibly energetic black holes, accreting vast amounts of matter. The idea was that these feedback mechanisms, the immense energy released during this accretion process, could have significantly suppressed star formation and ultimately limited the growth of galaxies. However, JADES GSC 14.0 defied this expectation, appearing to be a relatively quiescent galaxy despite its tremendous distance and redshift. This suggests that other processes, perhaps simpler stellar feedback mechanisms, or inherent properties of the galaxy's gas content, were more influential in shaping its evolution. The initial NIR spec measurements sparked further investigation using the Atacama Large Millimeter/Submillimeter Array, or ALMA. ALMA, with its unmatched ability to detect faint millimeter wavelength radiation, observed ionized oxygen within JADES GSC 14.0. This detection provided a powerful confirmation of the redshift measurements and allowed for a more refined determination of the galaxy's properties, solidifying the redshift value to 14.1793 plus, or minus 0.0007. The subtle presence of ionized oxygen, indicating active star formation, underscores the dynamic nature of these early galaxies. It is important to note that while JADES opens redshift 14 presents a compelling case for two remarkably luminous galaxies at such an early epoch, it does not represent the entirety of what JWST is revealing about this period. The survey continues to uncover dozens of other high redshift galaxies, each with its own unique characteristics and challenges in interpretation. Each new observation pushes us closer to understanding the fundamental processes that governed the formation and evolution of cosmic structures. Furthermore, these early galaxies challenge some long-held assumptions about the chemical enrichment of the universe. The presence of elements heavier than hydrogen and helium, so-called metals, is a critical indicator of how stars have lived and died, and dispersed their processed material throughout space. It is surprising to find such complex chemistry already present in galaxies just 300 million years after the Big Bang, suggesting that star formation was happening much more rapidly than previously thought. The detailed study of JADES GSC 14-0 and its contemporaries is therefore providing invaluable insights into the conditions necessary for chemical evolution in the nascent universe. And while the black hole accretion hypothesis has not been entirely ruled out, it still represents a viable possibility for some galaxies at these redshifts. JADES opens Redshift 14 serves as a crucial reminder that the early universe was likely far more diverse and complex than initially envisioned. The faint light from these ancient galaxies offers a glimpse into alternative pathways of galaxy formation, challenging our current models and urging us to refine our understanding of cosmic evolution. It is a slow unfolding, a delicate piecing together of information across billions of years, and JADES is providing an extraordinary chapter in that ongoing narrative. It stands as evidence of the persistent curiosity driving humanity's exploration into the vastness of space and time, seeking answers to questions posed by the universe itself. The survey was JADES, the JWST Advanced Deep Extragalactic Survey, and the decisive spectrum came from Webb's own NIR spec instrument. Let us consider the deep night sky, a canvas speckled with the distant light of galaxies born billions of years ago. We are reaching back to an era when the universe was incredibly young, a time shrouded in mystery, a period we call cosmic dawn. And recently, thanks to the astonishing capabilities of the James Webb Space Telescope, that dawn is beginning to illuminate itself for us in remarkable detail. Today's observation focuses on MZ14, a galaxy so distant, so ancient, that its light has traveled nearly 13.5 billion years to reach our instruments, carrying with it echoes of the very first stars and galaxies. MZ14 sits within the established cosmos field, a carefully chosen region of the sky meticulously surveyed by the Mirage or Miracle Survey. Projects designed specifically to hunt for these incredibly faint and distant objects. It was not simply found. It was identified through painstaking searches among countless other candidates, a testament to the dedication of those mapping the infant universe. The initial discovery relied on broadband photometry, establishing its general location relative to other galaxies before JWST spectroscopic observations could confirm its truly extraordinary redshift. This is important to understand. Much of the groundwork for these discoveries relies on prior surveys, refining our focus onto specific areas of interest. Now let us turn to the data itself, the heart of what makes MZ14 so compelling. Using the near-infrared spectrograph NIR spec prism mode on Webb, scientists measured its spectroscopic redshift, a value that describes how much the light from this galaxy has been stretched due to the expansion of the universe. This resulted in a remarkable Z-spec equals 14.44 plus, or minus 0.02, an incredibly high number, translating to approximately 280 million years after the Big Bang. To grasp the scale, MZ14 represents a snapshot of the universe only about 280 million years after the Big Bang, a truly early moment in cosmic history. But redshift alone does not paint a complete picture. What you see here, what we can directly measure through spectroscopy, tells us about the composition and processes happening within this distant galaxy. The spectrum reveals a distinctive Lyman alpha break, a sharp drop in intensity at a specific wavelength, a hallmark of young galaxies actively emitting ultraviolet light. Adding to this are several approximately 3 sigma rest ultraviolet lines. These represent faint but detectable signatures from different elements, indicating the presence of hydrogen and other ionized gases within the galaxy's vicinity. These are not just theoretical predictions. They are tangible features embedded in the light itself. The source is remarkably compact, a tiny point of brightness against the vast backdrop of space. And critically, its ultraviolet slope is deeply blue, a characteristic that suggests minimal dust obscuration. Dust, when abundant, tends to dim and redden starlight as it passes through. The absence of significant dust scattering indicates that this galaxy's young stars are emitting a tremendous amount of UV radiation with little interference. Furthermore, we observe evidence for rapidly rising recent star formation. The galaxy is actively building its stellar mass at an astonishing rate, burning through its fuel supply with remarkable intensity. It is as though the universe is accelerating itself into existence at this epoch. The scientific papers describing MZ14 present some intriguing and slightly surprising results regarding bright source abundance. Researchers report that its overall brightness, specifically in ultraviolet wavelengths, is significantly greater than what prevailing models predicted for galaxies at such redshift levels. These older theoretical frameworks assumed the early universe was comparatively darker, with fewer heavy elements dispersed throughout space. MZ14 challenges this consensus, hinting at a far more dynamic environment than previously envisioned. However, it is crucial to recognize that a single galaxy, and even a single survey focusing on a particular field, cannot definitively rewrite cosmological models. The sample size is simply too small for such sweeping conclusions. These findings stimulate further investigation, encouraging scientists to refine their understanding of how early galaxies formed and evolved. The implications ripple outwards, touching upon the processes of reionization, the period when the first stars and galaxies began to ionize the neutral hydrogen gas that permeated the young universe. The intense UV radiation from these nascent objects is believed to have triggered this process, gradually stripping electrons from hydrogen atoms, transforming the universe from a dark soup into the transparent medium we see today. MZ14's brightness and characteristics provide valuable insight into the mechanisms driving reionization, helping us understand how quickly and efficiently the first galaxies seeded the cosmos with their light. Furthermore, MZ14 suggests there may be more such incredibly bright galaxies out there, lingering undiscovered in deep field observations. It pushes us to refine our techniques, to develop even more sensitive instruments and sophisticated data analysis methods, to continue probing the distant past. The universe is still holding its secrets close, offering glimpses of a time when everything was new, when the threads of cosmic structure were just beginning to be woven. The work also speaks to the broader picture of early black hole formation. As these first galaxies grew and merged, they inevitably formed supermassive black holes at their centers. Though how these seeds of behemoths came to exist remains one of cosmology's most profound mysteries. The intense star formation in MZ14 likely played played a significant role there too. The observations offer clues as to the conditions under which such galaxies assembled and subsequently hosted their central gravitational engines. Ultimately, MZ14 is not just another faraway galaxy. It is an anchor, a point of reference in the early universe, a testament to Webb's capability, and a catalyst for ongoing research. The distance provides a particularly clear signal. It represents a crucial piece of the puzzle, demanding we reconsider our assumptions about the universe's infancy, and prompting us to ask challenging new questions about its creation. The journey through these distant epochs continues, each observation bringing us closer to unraveling one of the most fundamental mysteries in existence. How did everything begin? As of this research cutoff, MZ14, not JADES 14.0, holds the spectroscopic distance record at Redshift 14.44. The universe began with a twilight, an epoch of profound darkness, broken by the first tentative flickers of starlight. For years, astronomers have been chasing this dawn, meticulously gathering data from telescopes across our planet, hoping to glimpse the infant galaxies that seeded the cosmos with the elements necessary for life as we know it. And now, with the extraordinary capabilities of the James Webb Space Telescope, we are seeing not just the light from those ancient sources, but a subtle dissonance, a puzzle that hints at deeper mysteries about how these earliest structures truly formed and evolved. We are increasingly discovering a surprising brightness in some of the very first galaxies, far exceeding what many theoretical models predicted. This is not merely an unexpected observation. It is a tension, a discrepancy that forces us to reconsider our fundamental understanding of cosmic evolution. Before JWST began its transformative observations, cosmological models built upon decades of data from Hubble and other instruments generally anticipated a much more subdued picture for galaxies at high redshifts, specifically around redshift 10. These simulations often suggested a sparser population of exceptionally luminous galaxies in the early universe, predicting that the average brightness of these primordia. The prevailing view was one of a gradual buildup, a slow accretion of matter, and subsequent star formation, leading to increasingly massive and luminous galaxies over cosmic time. However, JWST data is presenting us with an immediate abundance of remarkably bright objects at precisely these formative epochs. Galaxies appearing brighter than expected based on our current understanding of the processes driving galaxy growth. The underlying reason for this apparent brightness anomaly lies in the nature of young star populations. Galaxies formed in the early universe were dominated by intensely active, short-lived star formation events. Stars born during these periods are characterized by a far greater abundance of massive, hot, ultraviolet-emitting stars than you would find in older stellar populations. These behemoths burn through their fuel incredibly quickly, measured in just millions of years, and produce an astonishing amount of energy, predominantly in the ultraviolet spectrum. It is like a cosmic firework display, concentrated within relatively small volumes of space. Consider it this way. Each unit of accumulated stellar mass in these young galaxies effectively generates far more light per unit time than the equivalent mass of stars residing in older galaxies. This is not simply a matter of individual star brightness. It is a fundamentally different mode of star formation, bursty, chaotic, and characterized by an overabundance of high-mass progenitors. Now, let us consider the complexities of observation itself. The process of measuring how bright these distant galaxies appear to us is riddled with uncertainties. The light from these ancient objects travels for billions of years across vast cosmic distances, encountering intervening clouds of gas and dust that absorb and scatter some of its photons. Nebular emission, the glow emitted by ionized gases within nebulae, can be mistaken for starlight, adding to the perceived brightness. Similarly, assumptions about dust content play a crucial role. More dust requires more light to escape a galaxy's interior, effectively dimming our view. Then there are active galactic nuclei, or AN, supermassive black holes at the centers of galaxies that actively accrete matter, emitting immense amounts of energy across the electromagnetic spectrum that can significantly inflate a galaxy's total luminosity. And finally, we have photometric degeneracies. The limited precision with which we can determine both a galaxy's distance and its intrinsic brightness creates ambiguity when comparing observations from different instruments or wavelengths. All these factors, alongside subtle effects related to how light bends around massive structures through gravitational lensing, can collectively alter our inferred mass estimates and distances, effectively boosting the apparent brightness of galaxies in certain samples. Crucially, simply looking at individual headlines, isolated examples of remarkably bright early galaxies can be misleading. The true picture emerges when we examine larger samples of data. Spectroscopic observations, which precisely measure a galaxy's redshift, an indicator of its distance, and chemical composition, provide far more reliable information than solely relying on photometric measurements' brightness determined from analyzing the colors of light received. Similarly, luminosity functions, plots showing the number of galaxies at various brightness levels within a specific volume of space. These large-scale statistics reveal whether these bright objects are truly representative of the overall early universe or represent a particular selection effect. It is important to recognize that revising galaxy formation models is a gradual process built upon accumulating evidence and refining our theoretical frameworks. It is not about abruptly overturning our current understanding of cosmology. Rather, it is about rigorously testing existing theories against new observations and adapting them as necessary. The bright early galaxies are not necessarily evidence that the fundamental laws governing gravity and the evolution of structure in the universe are wrong. Instead, they may signify the need to incorporate more sophisticated mechanisms into our models, perhaps a greater emphasis on the role of bursty star formation, feedback from AGN, or even entirely new physical processes we have not yet identified. The challenge lies in disentangling these complex effects and precisely quantifying their influence on observed galaxy properties. This requires continued observations with instruments like JWST, coupled with increasingly ambitious theoretical simulations. As we gather more data and develop more refined models, we will gradually peel back the layers of uncertainty surrounding the dawn of galaxies, ultimately unlocking a deeper understanding of our cosmic origins. The current tension represents not an ending, but a redirection, a compelling invitation to delve further into the intricacies of the universe's infancy, pushing the boundaries of what we know and challenging us to refine our perspective on how these first faint lights ultimately illuminated the cosmos as we see it today. Too bright for an old forecast is not the same statement as impossible in the universe. The light from these ancient galaxies arrives at us now as a faint whisper across billions of years, stretched by the expansion of space itself. But within that whisper lies an astonishing concentration of energy. we are focusing today on something exceedingly compact, what we call compact powerhouses. And it is a concept central to understanding how the very first structures in our universe began to take shape, how these nascent galaxies grew so rapidly, and what they tell us about the processes that eventually brought forth everything around us. Consider for a moment the sheer scale of cosmic distances. Light, traveling at its relentless speed, takes years, decades, even millennia to reach Earth from distant galaxies. The images we receive are, therefore, not direct snapshots of these objects as they were when they first ignited their luminous flames, but frozen echoes of moments long past. And within those echoes, a surprisingly small size reveals volumes about the processes at play. The effective radius, what you might think of as the edge of these primordial galaxies, is frequently only hundreds of parsecs across. Now, a parsec is roughly 3.26 light years, and so imagine a region of space less than 1,000 light years in diameter, containing an entire galaxy, one that was actively forming and shedding intense radiation just a few 100 million years after the Big Bang. It is fundamentally different from the spiral or elliptical galaxies you see clustered around our own Milky Way. Those behemoths composed of hundreds of billions of stars spread across tens or even hundreds of thousands of light years. These early galaxies were dramatically more condensed, pockets of immense stellar density. And it is this compact nature that immediately unlocks a deeper understanding of the phenomenal growth they underwent. This extreme compactness inevitably leads to incredibly high stellar and gas surface densities, meaning there are an extraordinary number of stars packed into a tiny volume of space, alongside a correspondingly large amount of gas, both hot ionized gas and cold molecular hydrogen, fueling further star formation. The interactions within this environment become profoundly intensified. Gravity acts with an unprecedented vigor. Collisions between gas clouds become far more frequent. The feedback mechanisms, the winds from massive stars, the jets from supermassive black holes at their centers, the radiation pressure from newly formed stars, all work with a ferocious intensity due to the proximity of everything. This creates incredibly short dynamical times, meaning that processes unfold remarkably quickly on galactic scales. It is like compressing an entire lifetime of star formation into a few million years, a period normally associated with the evolution of much larger galaxies. Of course, establishing these physical parameters, how small they were, how dense they are, is only part of the story. The data we receive from instruments like the James Webb Space Telescope is not a perfectly sharp image. The extreme distances involved introduce significant blurring and distortion into the observed light. What appears as a point on the detector represents not just a single object, but an entire galaxy, a complex aggregation of stars, gas, and dust, spread out over a considerable physical region. The resolution, our ability to distinguish fine details, is fundamentally limited by what is known as the point spread function, which describes how light from a point source is spread across the detector due to the telescope's optics. Furthermore, gravitational lensing effects can magnify and distort these distant galaxies further, creating multiple images of the same object, each with its own varying brightness and shape. To accurately interpret what we are seeing, astronomers employ sophisticated lens models, meticulously accounting for the gravity of intervening galaxies and galaxy clusters to reconstruct the true morphology, the appearance of these faint objects. It is a process that blends observation with informed inference. We can see the effects, the bright cores, the distorted shapes, but directly tracing an individual star from its birth in one compact galaxy to its eventual fate as a white dwarf or neutron star across billions of years is, for all practical purposes, impossible. The universe has expanded so dramatically that the vast distances between these objects have grown beyond comprehension. We are essentially trying to piece together a jigsaw puzzle where many of the pieces have been scattered to the very edges of existence and separated by incomprehensible gulfs of space. Nevertheless, scientists suspect that some of these early compact powerhouses served as progenitors, the seeds, for larger galaxies that we observe today. The intense star formation rates they experienced, combined with their dense environments, may have fostered mergers and accretion events, gradually building up mass and complexity over time. It is a gradual process of accumulation, a cosmic layering, where smaller, compact structures contribute to the evolution of grander galactic forms. The similarities in spectral signatures, the patterns of light emitted by distant galaxies, suggest that many share fundamental properties with these early proto-galaxies, solidifying this hypothesis. The chemical enrichment is another crucial element here. As stars die and explode as supernova, they scatter heavy elements forged within their cores into the surrounding space. These elements provide the building blocks for future generations of stars and planets. The intense star formation rates in compact galaxies mean that these elements were quickly recycled back into the interstellar medium, creating a richer environment in which subsequent generations could form. It is a constant cycle of creation and destruction, fueling the growth of the universe from its earliest moments to the complex tapestry we see today. We are also beginning to understand how these galaxies influenced the broader cosmos. They played a role in reionization. In the very early universe, it was dark, essentially devoid of light. Then, as these first galaxies began to shine with intense ultraviolet radiation, this energy ionized the neutral hydrogen that permeated space. This process, reionization, marked a profound shift in the universe's evolution and changed the conditions through which later galaxies developed. The limits of current cosmology are intrinsically linked to our ability to observe these distant objects. The farther away we look, the greater the redshift, the stretching of light due to the expansion of space becomes. This not only affects the observed wavelengths of light, but also introduces significant uncertainties in distance measurements. Understanding how these early galaxies fit into the larger cosmological framework, how they contributed to the formation of dark matter halos and the development of cosmic voids, remains a central challenge for astronomers. As we continue to refine our understanding of JWST data, we will likely uncover even more surprising details about these compact powerhouses, their internal dynamics, their star formation histories, and their connections to the broader evolution of the universe. It is through this study that we begin to truly grasp the genesis of everything around us, a slow, intricate process beginning in the darkest corners of an ink. On the detector, these galaxies can be only a handful of useful pixels. Yet inside those pixels, matter is assembling at extraordinary density. Let us consider a moment the vastness of time, stretching back to an era before galaxies, as we know them, existed, before even the faintest glimmer of starlight pierced the darkness. The universe immediately following the Big Bang was dominated by hydrogen and helium, the very first elements forged in the crucible of that initial expansion. Trace amounts of lithium were present too, remnants from a fleeting period of nucleosynthesis. But the abundance of heavier elements, particularly oxygen, was remarkably low. It was not a cosmic ocean brimming with the stuff that would ultimately form planets, stars, and eventually you. The early universe lacked the critical building blocks for widespread oxygen creation. Think of it like this: the Big Bang laid down a foundational material palette, mostly hydrogen and helium, alongside tiny hints of lithium. The vast majority of what you breathe, the oxygen within your body, is not a product born directly from that first spark. It is a story unfolding over billions of years, one meticulously woven through stellar processes and explosive events. The journey to a universe saturated with oxygen began long before it seemed possible, hidden within the hearts of stars themselves. Stars are essentially gigantic furnaces, converting hydrogen into helium in their cores, a process known as nuclear fusion. But this is not just about producing helium. It is a complex chain reaction that yields progressively heavier elements: carbon, nitrogen, and ultimately oxygen. The mass of a star dictates which elements it can produce, the conditions within its core determining the pathways available for these reactions to proceed. Massive stars, those behemoths collapsing under their own gravity, burn through their fuel much more rapidly than smaller ones, forging an abundance of heavier elements in their dying moments. These heavier elements are not simply created and then left behind. They are scattered across space by a variety of mechanisms. Through stellar winds, streams of charged particles flowing from the star's surface, lighter elements like carbon and oxygen are expelled into the interstellar medium. Then, when stars reach the end of their lives, particularly those that are massive and unstable, they undergo dramatic explosive deaths, supernova. These cataclysmic events scatter even heavier elements across vast distances, enriching the material available for future star formation. It is a continuous cycle of creation and dispersal, a cosmic recycling process driven by gravity and nuclear physics. Now, let us turn our attention to a specifically powerful tool in this investigation: the O-Roman-3 88 micrometer line. This signature of ionized oxygen is incredibly valuable because it does not just tell us where there is oxygen, but also how far away that oxygen originates, its redshift. Redshift describes how much the light from a distant object has been stretched by the expansion of the universe. Greater redshift indicates a greater distance and an earlier time in the universe's history. The O Roman 3 line is particularly useful because it is relatively bright and easily detectable, allowing astronomers to pinpoint regions where oxygen ionization is occurring. It acts like a spectral fingerprint, tracing the paths of ionized oxygen back through cosmic space. Recent observations using the Atacama Large Millimeter/Submillimeter Array, ALMA, have yielded particularly compelling data regarding this early oxygen enrichment. Measurements of the O Roman 3 line at high redshifts, specifically around C equals 14, have revealed that oxygen abundance was present surprisingly quickly in the very early universe, even before 300 million years after the Big Bang. This was a surprising finding, suggesting star formation and chemical enrichment were occurring much faster than previously thought. However, it is crucial to understand this does not uniquely date the first stellar population. It simply indicates that oxygen production began relatively early on. It is a snapshot frozen in time, revealing a process underway, but not necessarily defining its origins entirely. The implication of these observations is not about pinpointing a single first star. That might be impossible to determine, but rather about understanding the pace at which the universe was becoming enriched with the elements essential for planet formation and life as we know it. It suggests that stars were rapidly synthesizing heavier elements and dispersing them throughout space, paving the way for future generations of stars and planets. It is important to acknowledge the role of dust in this story. Dust, tiny particles composed primarily of carbon and silicon, plays a significant but often misunderstood part in star formation. While it certainly affects cooling processes within molecular clouds, the vast, cold regions where stars are born, allowing them to collapse under gravity, it does not directly fuse hydrogen into oxygen. Dust grains act as catalysts and scaffolding, providing surfaces for molecules to form and increasing the likelihood of certain reactions occurring. But they are not themselves contributors to the elemental makeup of stars. The heavy elements, including oxygen, are forged within the star itself through nuclear fusion. Think about it like building a house. Dust provides the framework, but you need bricks and mortar, the actual materials, to construct the walls. Similarly, dust helps facilitate star birth, but the creation of heavier elements is intrinsically linked to the processes happening within the star's core. Oxygen, in particular, requires the intense heat and pressure found deep inside a massive star before it can even begin to be produced through fusion. The early universe was not simply filled with hydrogen and helium waiting for an external trigger. It was actively being shaped by stellar evolution, driven by gravity and fueled by nuclear reactions. The detection of oxygen at these high redshifts does not rewrite our understanding of the Big Bang itself, but it powerfully demonstrates how quickly and surprisingly rapidly the universe transitioned from a primordial. It tells us that the seeds of planets, and perhaps even life, were sown remarkably early in cosmic history, driven by the dazzling yet utterly silent work happening within those first flickering stars. The journey continues as we collect more data, refine our models, and strive to piece together the complete narrative of our universe's evolution. A story written not just in light, but in the very fabric of space and time. The oxygen line is evidence of prior stellar processing. It is not a label telling us exactly which stars lived and died. The universe, as we perceive it today, is filled with a surprising amount of nitrogen. It is a fundamental element, essential for life as we know it. Yet its presence in those incredibly early galaxies offers a persistent and compelling puzzle. We've been steadily adding to our understanding through the incredible data streaming from the James Webb Space Telescope. And recently, two particularly intriguing observations have shifted our perspectives on the very beginnings of cosmic chemistry. GS 3073 and MO MZ14. It is important to approach these discoveries not as definitive answers, but rather as exquisitely detailed clues, illuminating pathways we can follow deeper into an epoch still shrouded in considerable shadow. Let us begin with GS 3073, a galaxy located at a redshift of approximately 5.55. This means the light we are seeing from it has traveled for over 10 billion years to reach us, offering a glimpse of the universe when it was roughly 1 billion years old. What immediately stands out is its startling nitrogen to oxygen ratio, an exceptionally high abundance compared to what current models predicted for galaxies of that era. it is not simply elevated, it is significantly above expectations, and further observation reveals a distinct chemical stratification. Different layers within the galaxy displaying varying elemental compositions. This suggests complex processes were at play from nearly the very beginning, far earlier than we typically assume. This extreme ratio has sparked much debate among astronomers, prompting us to consider alternate pathways for the synthesis of these heavier elements in those primordial environments. Then there is MZ14, another remarkably distant galaxy caught in the Webb's gaze at a redshift around 7.6. This object presents its own set of tantalizing mysteries. Notably, it exhibits nitrogen emission lines, a clear indicator of the presence of nitrogen atoms, and possesses a surprisingly high inferred nitrogen to carbon ratio. The data suggests this ratio is markedly higher than what would be expected based on typical star formation models. Adding to the intrigue is the possibility that MZ14 resides within a dense cluster of galaxies, potentially influencing its chemical environment and fueling further speculation about the origins of these elevated nitrogen levels. It is as if these early galaxies were experimenting with their elemental inventories in ways we had not fully anticipated. Now, to understand these unusual observations properly, we must first delve into something called population Roman 3 stars. These are considered the very first stars, the primordial ancestors of everything that followed. They represent a unique class of objects because, unlike every star formed since then, they were metal-free. That means they did not contain heavier elements, anything beyond hydrogen and helium, formed in the cores of previous generations of stars. Their formation was purely through nuclear fusion of just those two elemental constituents. Their masses, and crucially, their eventual endpoints, whether they ended as supernova or gently faded away as white dwarfs, remain a matter of ongoing research and model development. There's no single, universally accepted picture. Simulations continue to refine our understanding of these elusive stellar entities and how they might have seeded the early universe with heavier elements. The fact that we have not directly observed a single population Roman 3 star is profoundly significant. It means we are working with theoretical models, complex calculations based on gravity, nuclear physics, and stellar evolution to infer their properties. And it is this inherent difficulty in direct detection that complicates the interpretation of these elemental abundance anomalies we see in early galaxies like GS 3073 and MO MZ14. Consider how elements are dispersed throughout the universe. The prevailing theory suggests that early star formation, specifically through supernova explosions, served as the primary mechanism for enriching the primordial gas with heavier elements. When massive stars die, they violently shed their outer layers back into space. These ejected material, heavy elements forged in their cores, mix with the surrounding interstellar medium, becoming incorporated into subsequent generations of stars and planets. This is often referred to as enrichment. However, when we observe these early galaxies, what we are actually seeing are indirect signs of enrichment. We detect the presence of heavier elements like nitrogen in the gas surrounding them, a consequence of this previous enrichment cycle. It is like tracing footprints back to their source without ever having seen the original walker. The high nitrogen to oxygen ratio in GS 3073 does not necessarily mean that population Roman 3 stars were directly responsible for producing all that nitrogen. It could be a result of subsequent non-metal enrichment processes, perhaps through interactions with other galaxies or complex chemical reactions within the early gas clouds themselves. Similarly, MO MZ14's elevated nitrogen levels could be linked to its dense cluster environment, where gas mixing and feedback from active galactic nuclei might have played a significant role. It is important also to understand that simply finding evidence of nitrogen, as we do in these distant galaxies, does not confirm the type or origin of the source of this element. The observed ratios could be products of processes vastly different than what the models for population Roman 3-star formation predict. They might represent contributions from a diverse range of stellar populations and mechanisms, perhaps Wolf-Rayet stars, which are massive, helium-rich stars known for their powerful winds that eject significant amounts of enriched material, or even asymptotic giant branch AGB stars nearing the end of their lives that undergo significant mass loss. All of these types of objects could have contributed to the observed elemental composition, though each with different characteristics and byproducts. Currently, no single result has definitively proven a direct detection of a population Roman 3 population. The data remains suggestive, but not conclusive. Instead, we are left with a more nuanced picture, an intricate tapestry woven from observations and theoretical models. The abundance of nitrogen in early galaxies like GS 3073 and MO MZ14, combined with our understanding of stellar evolution and enrichment mechanisms, is pushing the boundaries of our cosmological knowledge. They're prompting us to reconsider everything from the initial conditions of the universe to the very processes that shaped its luminous evolution. As we continue to gather data, especially as Webb's capabilities expand, we will undoubtedly unravel more secrets about this primordial era, inching closer toward a truly comprehensive understanding of how the cosmos came to be filled with the elements upon which life, a chemical fingerprint can narrow the suspects without identifying a single culprit. The universe whispers its secrets slowly, revealing them bit by bit as our instruments grow ever more sensitive. Today's focus is on that faint, nascent murmur, the echoes of cosmic dawn, a time when the first galaxies began to ignite, scattering their light across the vast expanse between us and the distant past. We are delving into the data from the James Webb Space Telescope, specifically exploring what it has unveiled about these early behemoths, the infant black holes that seeded the growth of everything we see today. The sheer scale of this endeavor is breathtaking, requiring us to consider distances so immense they challenge our everyday understanding of time and space. Let us begin with a look at one particular, crucial probe into this era, the JADES JWST, Advanced Deep Extragalactic Survey Broadline and Sample. This survey, meticulously crafted by teams around the world, has already yielded extensive information about galaxies at redshifts between 4 and 7, a window into the universe when it was roughly 800 million to 1.5 billion years old. And crucially, it is not merely adding to our knowledge. It is radically reshaping what we thought we knew about these early galaxies. Alongside this, the GNZ11 galaxy, at an astonishing redshift of 10.6, continues to serve as a beacon in the darkness, providing invaluable data points for understanding fundamental processes. The initial reports from JADES noted 12 broadline active galactic nuclei, and within this redshift range, alongside the already known AN residing within GNZ11 itself. These AN are not simply distant galaxies with unusually bright centers. They represent galaxies actively feeding their central supermassive black holes, consuming immense quantities of gas and dust in a process that profoundly influences their surroundings. Now, let us consider what we can infer about the mass of these nascent black holes. Black hole mass estimates derived from observations are inherently complex, relying on sophisticated models and assumptions. However, based on current data analysis, the inferred masses range significantly, typically falling between approximately 400,000 and 80 million solar masses. That's a span encompassing orders of magnitude, reflecting the considerable uncertainties involved in these calculations. It is important to acknowledge that directly weighing a black hole is fundamentally impossible. Instead, we rely on observing their gravitational influence on nearby stars or gas clouds. This indirect measurement method, while incredibly powerful, introduces its own set of potential biases and limitations. We are essentially inferring the weight of something invisible with the visible movements of things around it. A delicate dance of observation and interpretation. Interestingly, some of these early black holes appear to be disproportionately massive relative to the stellar mass of their host galaxies. This finding is particularly perplexing when compared to the distribution of black hole masses in galaxies we observe today within our own local group. The black holes of our Milky Way, for example, generally follow a predictable correlation with the size and mass of the galaxy they inhabit, a relationship known as the black hole mass function. However, these early ANs seem to buck this trend, exhibiting an overabundance of massive black holes compared to their host galaxies. This disparity prompts fascinating questions about how these colossal black holes could have formed so rapidly in such young galaxies. The seeds of these burgeoning giants, the pathways through which they grew to such immense sizes, remain shrouded in a degree of mystery. Several competing hypotheses are currently being explored by astrophysicists, each offering a plausible explanation for this observed discrepancy. One leading idea suggests that black holes formed from light seeds, tiny remnants of dead stars, stellar corpses ejected during the early universe's supernova explosions. These light seeds then grew through mergers with other smaller black holes and accretion of gas, steadily increasing in mass over time. Alternatively, Another pathway posits that heavier black hole seeds formed directly from collapsing cores of massive, early stars, a process known as direct collapse. This scenario would have allowed for the formation of larger seeds without requiring extensive merger events. Yet another possibility focuses on rapid black hole growth through mergers with smaller black holes and accretion of gas at rates significantly above what is typically observed today, a phenomenon dubbed Eddington or super Eddington growth. It is crucial to understand that all of these hypotheses are vying for dominance, and currently there is not a clear winner. Each offers potential advantages and faces significant challenges in explaining the full range of observations we are receiving from JWST and other telescopes. The exact mechanisms responsible for the initial formation of these behemoths, whether they originated from stellar remnants, direct collapse, or rapid accretion, remain among the most compelling questions in cosmology today. Adding another layer of complexity to our understanding is the fact that broad H-alpha emission, a characteristic spectral line produced by hydrogen gas, reveals only a portion of the active pop. An activity profoundly affects the surrounding environment, obscuring much of the star formation through copious amounts of dust and gas, a phenomenon known as dusty toral occultation. Moreover, selection biases inherent in our observational methods can inadvertently exclude certain types of AN from our catalog, meaning we may be underestimating their true abundance. Think of it like shining a flashlight. You only see what is directly illuminated. The obscured regions hold vital clues about the overall activity and evolution of these early galaxies. Furthermore, the distribution of black hole mass does not necessarily reflect the inherent properties of the host galaxy itself. Instead, it can be profoundly influenced by accretion rates, how quickly gas is feeding the central black hole. A galactic environment rich in readily available fuel will lead to higher accretion rates and, consequently, a larger black hole overall. This creates a feedback loop where the actions of the black hole dramatically shape the evolution of its host galaxy. The data from JWST continues to refine our understanding, pushing at the very boundaries of current cosmological models. It is forcing us to reconsider fundamental assumptions about the formation and growth of galaxies and their central engines. The supermassive black holes that now dominate the centers of most large galaxies. As we gather more observations, refine our theoretical frameworks, and develop increasingly sophisticated analytical techniques, we can expect even deeper insights into these formative years of the universe, a period where the seeds of everything we know were being sown. The coming years will undoubtedly reveal further surprises, continuing to unravel the grand cosmic narrative in stunning detail. Webb can reveal an actively feeding black hole, but the spectrum does not preserve a photograph of the seed from which it began. The universe began in darkness, a profound and absolute absence of light. Then, after an unimaginable expanse of time, nearly 13 billion years, something shifted. The first stars ignited, colossal beacons blazing into existence from within nascent galaxies. And as they shone, they cast their ultraviolet light outward, driving a process that would reshape the cosmos itself: reionization. Let us consider now the subtle and complex dance between these early stellar sources and the vast expanse of neutral hydrogen that filled the universe at that time, a period we have come to call cosmic dawn. The initial ionization was not uniform. It happened in patchy, irregular bursts. The ultraviolet photons emitted by massive stars and particularly energetic active galactic nuclei, or AN, supermassive black holes actively feeding on surrounding material, collided with neutral hydrogen atoms, stripping away their electrons and transforming them into ionized plasma. These encounters created immense, expanding bubbles of ionization, like ripples spreading across a dark ocean. And as these bubbles inflated, they intermingled with regions still dominated by neutral gas, creating an ever-shifting landscape of light and darkness. It is important to recognize that this process was not a simple, instantaneous event. It unfolded over hundreds of millions of years, driven by the continuous birth of stars and the relentless flux of UV radiation. The early universe lacked the heavy elements needed to absorb ultraviolet photons efficiently, allowing the ionization fronts to propagate further into the darkness. Imagine for a moment how incredibly distant these events, where light has been traveling for almost as long as time itself, to reach us from these primordial epochs, carrying with it whispers of the dawn. A critical tool in understanding this era is something called damped Lyman alpha absorption. This phenomenon arises when light from quasars extremely luminous AGN passes through intervening clouds of neutral hydrogen. The hydrogen atoms absorb certain wavelengths of ultraviolet light, causing a characteristic dampening effect on the observed spectrum. While primarily associated with the intergalactic medium, the space between galaxies, these dense reservoirs of neutral gas can also produce damping features. This means that the distribution and density of this neutral hydrogen are far more complex than previously imagined, and studying these absorption lines allows us to probe the conditions surrounding early galaxies as they formed. The signal is faint, requiring meticulous analysis, but it provides a valuable window into the dynamics of that early universe. Recent observations from JWST Primal have been particularly illuminating. This ambitious survey has mapped the ultraviolet spectra of thousands of galaxies at redshifts between 5.5 and 13.4, pushing back to an astonishingly early stage of cosmic evolution. And what they have found is remarkably consistent. Strong absorption features associated with damped Lyman alpha, indicating that substantial fuel reservoirs, regions of dense neutral hydrogen, existed around many of these young galaxies. This strongly supports the idea that reionization was a protracted process, driven by countless individual stellar sources and AN interactions. It suggests that there were far more local sites of ionization than previously thought, contributing to the patchy nature of this cosmic dawn. However, our understanding is not yet complete. A tantalizing clue comes from observations of MZ14, a galaxy at redshift 14.44, one of the most distant galaxies ever observed. Researchers have analyzed its absorption spectrum and found that the damping wing, the feature indicating the density of neutral hydrogen around the galaxy, is unexpectedly weak. This suggests a less dense, partially ionized environment surrounding MZ14 than would be expected if the universe were uniformly filled with ionized gas at that epoch. It is like noticing a patch of quieter water in an otherwise turbulent sea. It hints that the overall picture is more nuanced and complex. It is crucial to acknowledge that AN activity likely played a significant role in reionization. Yet, quantifying their contribution remains a challenge. Their luminosity function, the distribution of AN brightnesses across cosmic time, is still being refined, And crucially, we do not fully understand how effectively they radiated ultraviolet light outwards. The ionizing escape fraction, the proportion of photons emitted by an AN that actually makes it out into intergalactic space, is highly uncertain. Modeling these processes requires considering complex interactions between black holes, their host galaxies, and the surrounding intergalactic medium. The prevailing theory suggests that both massive stars and energetic AN were key players, each contributing to the ionization in distinct ways. The early universe was a chaotic mixture of stellar radiation and the powerful emissions from supermassive black holes. And as these bubbles of ionization expanded, they gradually overwhelmed the pre-existing sea of neutral hydrogen, shifting the balance towards a more luminous and ionized cosmos. It is a remarkable transformation, a slow but profound shift in the fundamental state of the universe that paved the way for the formation of galaxies like our own. The ongoing research into these early epochs continues to refine our understanding of this pivotal period. Future observations with JWST, as well as other advanced telescopes, promise to reveal even more details about the distribution of neutral hydrogen, the activity of AGN, and the evolution of the first galaxies. Each new discovery brings us closer to unraveling the mysteries of cosmic dawn, to glimpsing the very beginning of everything we know. And the universe itself continues to patiently unveil its secrets across unimaginable stretches of time and space. A clear path around one galaxy would not mean that the whole universe had already cleared. The echoes of the Big Bang still resonate, a faint hum within the vastness. And as we continue to peer further back into that ancient light, we find ourselves encountering snapshots of an unimaginable early universe. Yesterday's discoveries are today's foundations for understanding how galaxies were born, how they clustered together, and ultimately, how the cosmos came to be as it is now. Let us turn our attention toward a particularly compelling instance of this process, a burgeoning structure revealed by the James Webb Space Telescope, a protocluster named A2744Z 7P9 OD, a cluster still in its nascent stages, some 600 and. The story begins with the light from an extraordinary collection of galaxies, 7 in total, gathered within a region defined by the colossal gravitational lens of Abell 2744, a massive collisionless void that acts as a cosmic magnifying glass, bending and distorting the light from more distant objects behind it. This particular vantage point, offered through JWST powerful infrared instruments, has allowed us to observe these galaxies at a redshift of approximately 7.88. Redshift is simply a measure of how much the light from an object has been stretched by the expansion of the universe. The further away an object is, and thus, the earlier we are looking back in time, the greater its redshift. It is like listening to a siren's song played at a lower pitch as it recedes. The sound, in this case, light, becomes longer and redder. At 7.88, we are witnessing these galaxies as they appeared just a tiny fraction of a billion years after the universe began its expansion. A time when the very fabric of space was still smoothing itself out. A truly remarkable feat to observe at all. This is not merely a random assortment of individual galaxies. Rather, it represents a region where galaxies have already begun to coalesce into an overdensity. A subtle but significant deviation from the smooth flow of matter in the surrounding intergalactic medium. To understand this overdensity, we need to consider that even at this early epoch, there were fluctuations in density, slight variations in the distribution of dark matter and ordinary gas. These initial perturbations, seeded by quantum fluctuations in the very early universe, acted as gravitational seeds, attracting more matter and eventually leading to the formation of larger structures. The A2744Z7P9 OD system represents one such node, a nascent concentration where gravity has begun to pull galaxies together, a cosmic embryo taking shape. The fact that this system exists at all is profoundly interesting. Simulations running on some of the most powerful supercomputers available consistently predict that such overdense regions are destined to grow into massive clusters, akin to the great clusters we observe today, but considerably more compact and younger. However, it is crucial to remember that these are projections, modeled futures, rather than direct historical records. We cannot simply look at a 2744Z 7P9 OD and declare with certainty how it will evolve over the next several billion years. Instead, we use these simulations as guides, helping us to understand the underlying physical processes governing cluster formation, the interplay of gravity, gas dynamics, and feedback from supermassive black holes at their centers. they offer a plausible pathway, a potential trajectory, rather than a definitive outcome. Adding another layer of intrigue is the observation of the system's Lyman alpha emission. This faint glow, produced by hydrogen atoms excited by ultraviolet light from the galaxies, is remarkably weak, suggesting a significantly neutral surrounding medium. The abundance of neutral hydrogen at this stage in the universe's history holds significant clues about the period known as reionization, the epoch when the first stars and galaxies began to emit enough ionizing radiation to strip electrons from hydrogen gas, transforming it from a neutral state to an ionized one. The weakness of the Lyman alpha signal suggests that this process was proceeding relatively slowly in TH. Consider for a moment what such a localized transition might imply. As these galaxies formed and interacted, they likely released vast amounts of ultraviolet radiation, which then scattered off the surrounding hydrogen gas. This scattering reionized that gas, pushing it into an ionized state. However, the relatively weak signal we observe at redshift 7.88 implies that this process was not yet complete, that a substantial fraction of the universe remained neutral. The A2744Z 7P9 OD system appears to be sitting within a region where this reionization began modestly and slowly, offering a glimpse into one of the most formative periods in cosmic history. The lens effect itself provides invaluable data about these early galaxies. JWST infrared capabilities allow us to probe their shapes and sizes with unprecedented precision, revealing details that would have been completely obscured by the telescope's predecessor, Hubble. This lensing magnifies the light from these distant sources, effectively creating multiple images of each galaxy, some stretched and distorted into arcs or rings. By carefully analyzing these lensed galaxies, astronomers can estimate their distances, masses, and star formation rates, essentially reconstructing their properties from the warped light they cast upon the foreground galaxies. Looking ahead, researchers plan to utilize the power of future telescopes, particularly a proposed extremely large telescope ELT, to study this overdensity in even greater detail. With longer observing times and increased sensitivity, ELT will be able to probe the faintest galaxies within a 2744Z 7P9 OD, allowing us to better understand their internal structure and star formation histories. Furthermore, techniques like weak lensing, analyzing subtle distortions of background galaxy shapes, can be used to map the underlying dark matter distribution throughout the cluster, providing a more complete picture of its formation and evolution. Each observation, each dataset builds upon our understanding. And so, as we continue our investigations into this young protocluster, we are not simply studying individual galaxies. We are examining a crucial component of an extraordinarily complex process, the genesis of cosmic structure itself. A 2744Z 7P9 OD stands as a testament to the fact that even in the very earliest moments of the universe, galaxies were already beginning to congregate and evolve, laying the groundwork for the rich tapestry of structures we observe today. From the spiral arms of our own Milky Way galaxy to the vast, interconnected web of galaxies that dominates the observable cosmos,